Hello class, this is Mr. Hart, and in this podcast we want to discuss circular motion. So we've been looking a lot at gravitational pull and orbits and things like that with gravity, and it's really hard to understand why orbits are the way they are unless we talk about circular motion first. Okay, so when you did the orbit lab last time, the My Solar System lab, you probably noticed that a lot of the orbits are not circular, they're elliptical, right? But it's really hard to talk about ellipses without having a good understanding of circular motion first. So even though it's an approximation, we're going to talk about circular motion when we're describing orbits of planets. Okay. But before we get to planets and all that stuff, let's just focus on what circular motion is and how we define it. So when we're trying to define circular motion, it has this very unique property. Okay, and that property is that if we look at the velocity of an object in circular motion and we look at its acceleration, they're always in opposite directions, or I should be more specific, perpendicular directions. Okay, they're always in perpendicular directions. The velocity goes this way and the acceleration goes this way. Okay, when the object is at this point right here, its acceleration will go that way and its velocity will go this way. When it's down here, its acceleration will go this way and its velocity will go that way. So no matter what direction this thing is facing, no matter what point in the circle it's at, it always has this property that the way that the object's moving and the way that it's accelerating are perpendicular. Okay. So this is interesting because an object that is accelerating constantly towards the center and has this velocity, if it's circular motion, it actually never changes its speed. Okay, the velocity and acceleration change directions, but it never changes its speed. The velocity changes direction, but its speed stays the same. So this realization was actually one of the reasons that Newton was able to discover his law of general gravitation. Okay, because you know that story where Newton's underneath the apple tree and the apple falls on his head and he's like, oh, there's gravity, right? That's how people tell it. That's not the real case. He was actually, according to legend, was actually looking at the moon at the same time that the apple fell on his head. And the question he asked was, why doesn't the moon fall to the earth like the apple just did? Okay, and that led him to understanding these things and understanding this principle that things that are constantly accelerating towards the center, if they have enough velocity, they move around the outside rather than moving towards the center. Okay, think about like a satellite, for example. Satellites are constantly above the earth, right? But in reality, they're constantly falling towards the earth. So this idea that something can be constantly moving towards the center and moving perpendicular at the same time and never changing its speed is the idea behind circular motion. Okay, so we're going to define this acceleration. We call it centripetal acceleration. Okay, and keep in mind that this acceleration isn't going to change the speed. It's just going to change the direction of the velocity. This object, whatever it is constantly falling towards the center. Okay. All right, so we're going to define this centripetal acceleration. Okay, so centripetal acceleration is a change of direction around the center caused by the centripetal force on an object. Okay, don't get this confused with centrifugal acceleration or force, which is not real. Okay, so a lot of people will say, oh, centrifugal force. Okay, that's what throws you to the side when you're playing corners, or what throws you to the outside of a merry-go-round. Okay, that's not real. Like we talked about in forces, that's Newton's first law, right? That's just inertia that's carrying you. There is no such thing as a centrifugal force. Only centripetal. Okay, only centripetal force for acceleration. Okay? So this is how you can imagine it, right? So an object going around in a circle, the centripetal force is what's basically holding it towards the center. So if this was like a yo-yo, for example, the string, the tension in the string is what's holding the yo-yo in its path. Okay? So people say, oh, the yo-yo is being thrust out by this centrifugal force, but that's not the case. It's fictitious. This doesn't exist. Okay? Only this arrow right here that's holding it in. Okay? All right, so we want to be able to calculate the centripetal force, not the centrifugal. There is no centrifugal force. Okay? But here is how we calculate centripetal force. Okay? So centripetal force, or force centripetal, okay, is equal to the mass times the velocity squared over the radius or the distance. So centripetal force This is mass. This is velocity, and if you want to be very particular, this is actually just the speed or perpendicular velocity. Okay? And this is the radius. Okay? So centripetal force equals mass times velocity squared over the radius. Okay? So this is pretty simple to work with. We just find the mass of the object, how fast it's going, and how far away it is. Okay? Simple enough. So, and that will calculate the centripetal force, or how strongly something is held towards the center. Okay. And if you think about what you saw with the orbits lab, this kind of makes sense, right? The farther away something was, it has a very large R. Okay. It wasn't held very tightly in its orbit. Okay. If something's very close, it has to speed up really fast in order to keep the same orbit, right? So if you kind of think about some of those things you saw in the orbit lab, you'll notice that this makes a lot of sense, that the radius and the velocity are going to determine how strongly things are held. Okay. All right, so let's go ahead and try an example problem. So we got that a 40 kilogram child is on a merry-go-round that has a radius of 1.5 meters and a velocity of 5 meters per second. What is the centripetal force on the child? All right, so we know that mass equals 40 kilograms. We know that the radius is 1.5 meters and the velocity is 5 meters per second. So we'll just plug those into our equation. Fc, or centripetal force, equals mass times velocity squared over r, which in this case is 40 times 5 squared, don't forget the squared, over r, which is 1.5 meters. Okay, put this in our calculator. So 40 times 5 squared divided by 1.5 gives us 667 newtons about. Okay? And there we go. There's our answer. So 667 newtons is how much force is put on that child. Okay? So just to check on units though, force centripetal equals mass velocity squared over r. If we think about mass, that's going to give us kilograms. Okay. Radius is going to give us meters. And then velocity squared is going to give us meters per second squared. So meters squared per second squared. Okay. One of the meters is going to cancel out. And when it's all said and done, you get kilograms meter per second squared, which makes sense because that's a Newton. Okay, so there we go. That's what we were expecting. Okay. All right. So again, pretty simple. Just plug in what you know, and you're good to go. Okay. Let's look at two variations of this. Okay. Well, first of all, realize that we're going to use this for a lot of examples. CDs, things, rotating, but we're going to use them for, not that one, this one. We're going to use them for planets and things like that, right? So we can look at things like the Earth has a mass this large and it has a speed of this and it has pulled on with this force. What's the distance between the Earth and the Sun? Okay, so before we do a problem like this, realize that we're looking for distance this time. So we're looking for r. We want to know what r equals. Okay. So before we do anything, let's resolve that equation for r. So instead of having Fc equals mv squared over r, let's move the r over here. So we get Fc times r equals mv squared. And then let's divide by Fc to get r by itself. So the equation we're going to start with is r equals mv squared over Fc, or centripetal force. Okay. So this is the equation we are given, but we can manipulate it slightly so that we're solving for r. Okay. So now with that information, let's finish this problem. Okay. So we know the mass of the Earth, we know how fast it's moving, and we know the force between the Earth and the Sun. Okay. So mass equals 5.97 times 10 to the 24 kilograms. The velocity is 30 kilometers per second, or 30,000 meters per second. And the force between the two objects is 3.58 times 10 to the 22nd newtons. Okay? All right, so now we're plugging those things into here. So that's going to give us 5.97 times 10 to the 24 times 30,000 squared over 3.58 times 10 to the 22nd. Okay? So pull out our calculators, and again, be very careful with scientific notation when you are putting things in. So we get 5.97 times 10 to the 24 times 30,000 squared all over 3.58 times 10 to the 22nd. Okay. So when we do that, we find that all that stuff is going to simplify down to 1.5 times 10 to the 11 meters. Okay. Or basically 150 billion meters. Okay. So that's how far away the Earth is from the sun. And if you put that on Google, you can check. That's actually how far away it is. Okay. All right. But pretty simple to work with. Let's look at one more variation that we'll see. And that's, instead of having or trying to find the radius or trying to find the force, let's see if we can solve a problem where we're trying to find the velocity. Okay. So let's resolve that equation for velocity. So you have Fc equals mv squared over r. If we're trying to solve for velocity, that's times the r over here. So Fc times r, and then let's divide the m. So we get Fc times r over m equals v squared. Okay, well, if that's the case, then we just square root both sides, and we get that v equals the square root of Fc times r over m. Okay. So that's how we can solve. Okay, you can either write that down or just know how to manipulate it, but that's how we can solve problems where we're trying to find this velocity or how fast something is spinning or something like that. Okay. Let's look at a cool example of this. Okay. Back in the old days when computers were kind of the new thing and CD drives were coming out, okay, they actually were trying to keep continuing to build on the CD drive and make it go faster and faster and faster. They're trying to improve it every day, you know. And you'll see like 8-speed or 24-speed CD drives. And eventually they got to a point where the CDs were spinning so fast that they didn't have enough tensile strength anymore, and they ripped to shreds inside the drive. Okay, which is why you haven't seen a CD drive get any faster anytime soon. Okay. So let's look at and actually calculate how fast something would have to be going to rip apart. Okay. So if you look at the tensile strength of a CD and how much force it can take about 2,610 newtons. Okay, so if we assume that the mass of a CD is 15 grams and the radius is 30 millimeters, how fast must that CD be spinning on the outside? Okay. So we know Fc is 2,610 newtons. Okay. We know that the mass is 15 grams, but it's 0.015 kilograms. And we know the radius is 30 millimeters or 0.03 meters. Okay. So using that equation we just solved, we're going to rewrite it like this because we're looking for velocity. So velocity equals Fc times r over m. Okay. Plug all that in. So we get the square root of 2,610 times 0.03 over 0.015. Okay. Pull out your calculator. Plug it into there. So we get 2,610 times 0.03 divided by 0.0, or 0.015. Take the square root of that. And you should get that this thing's spinning pretty dang fast. Okay, all that stuff is going to simplify down to 72.25 meters per second. Okay, so that thing's zooming. Okay, it's going faster than your car goes down the highway, especially for something that small. Okay, but a great example of how we can solve for velocity. In class, we actually watched a video of a CD ripping apart, which is pretty fun. But anyways, that's all we're covering for today is centripetal force. So now you should be able to do it where you find the force or the radius or the velocity. Okay, and we're just kind of manipulating this equation. And in the next lesson, we'll see how we can kind of use this equation to describe orbits. Okay, but that's all for today. Let me know if you have any questions, and thank you for watching.